Hello and welcome back. In section 13.4, we look at trees. So what is a tree? Well, we have to have a connected graph. That's one of the requirements. Every edge is also a bridge. In other words, any one edge removed creates a disconnected graph. And these are used in various applications. You've seen family trees. Those are examples of connected graphs where every edge is also a bridge. Let's see, connecting new and remote areas to power grids. They tend to use trees to get the power going to the area in the least expensive way possible, and then they can sort of build it from there. But if they set up the system as a tree, it's the quickest, most cost-effective way to bring that to the area. So some example of graphs that are trees and some counterexamples, graphs that are not trees. So this is an example of a tree. Here's another tree. So removing any one of these edges, I no longer have a connected graph in either of these examples. Probability tree diagrams, another fun topic. Typically we draw those sideways, but that's sort of the basic setup. So those are some examples of graphs that are trees. Now let's take a look at a few that are not trees. This triangle. If I remove this edge, I still have a connected graph. I still have a way to get from, say, A to C. Let's see. This graph too, if I remove the loop, I still have a connected graph, so this is not a tree. In general, any graph that has a closed figure in it is not going to be a tree, although that's not the only type of graph that is not considered a tree. Bravo, Charlie, Delta, and Echo. If this is all one graph, also not a tree, because remember, a tree has to be a connected graph. This one is not a connected graph. So therefore not a tree. The other one simply had edges that could be removed and still give us a connected graph. So next, I'm going to look at one where I again do a little bit of labeling. I'll pause G, H, I, J, K, and L. So first off, is this a tree? And hopefully we recognize that no, this is not a tree. There are several edges that can be removed, and I would still have a connected graph. So while it does have one bridge, HI, actually at the moment no other edges are bridges. But key question here, can we remove edges to create a tree? In this case, since this is connected, yes. The previous graph, there's nothing I could do with this removing edges that would then make this into a tree. But if I want to remove edges from this, as long as it's a connected graph, I can get the job done. So some examples of what that might look like. If I remove FH, and also remove IL. Now every single edge is a bridge. Remove any of these and you have now a disconnected graph, but the one that we have at the moment is connected. That's not the only way we could have gotten a tree out of this. Maybe I instead could remove FG. And what else did I pick? IJ. Any of those removed makes our connected graph into a disconnected graph. If we're able to do this, if we're able to create a tree from a graph that previously was not a tree, that's what's referred to as a spanning tree. Let me go ahead and slap those labels back on there. So the second one, we remove FG and IJ. Not the only ways we could do it, but those are just two examples of how we could create spanning trees from these. So next up, I'm going to have you all try one out. So I'm going to make a bigger graph here. I'll do basically kind of an octagon setup. And let's see, we'll make a 2-degree vertex out of A, 2-degree vertex out of B, connect Foxtrot and Echo. Charlie will connect to Just Hotel, degree 1. Delta will connect that guy to Golf as well. Echo is already hooked to Bravo. We'll also hook him to Golf. Foxtrot will connect to Hotel. And Golf. 3. Okay. So I'm going to set up a few questions, then I'll ask you to pause it and try it out. So is this a spanning tree? If not, can it be made into a spanning tree? And if so, how? Okay, so go ahead and pause it, see if you can create or answer these the 3 questions here. Okay, welcome back. So first thing I want to check is to make sure that this graph is indeed connected. So for example, make sure that we can get from A to anywhere else. So if I want to get from A to B, let's see, I'd go through D and G and E up to B. I can hit C if I continue that journey. From B, I would go to F to H to C. I can go directly from A to D. I can go from A to E. We've seen that already. We'll get to B and down to E. Get to F. Let's see, we can get there from B. A and G are directly hooked up. So this one is a connected graph. It is not a spanning tree, however, because removing AD, we still have a connected graph. So it is not currently a spanning tree. Yes, it can be made into a spanning tree because it is connected. And if so, how? Well, there are several different examples of spanning trees we can make there. HC is already a bridge, so I like to just kind of start by keeping those guys. You don't have to keep the original orientation as well. You can rotate things. So from H, we would have to connect to F. From F, we would still have to connect to B. From B, we would still have to be able to connect to E. From E, we would still have to connect to G. G, we have choices though. Now I can go to A or to D. Neither of those would create a graph that is no longer consisting just of bridges. So let's go to A, then to D, and let me check them off as we go. So Hotel, Foxtrot, Bravo, Echo, Golf, Alpha, and Delta. So that is one example of a spanning tree. Again, not the only one, but it's one of the spanning trees we could make. So what did we remove? Let's see, we no longer have, let's see, A is still degree 2. D is down to degree 1, so we removed DG. E is still degree 2. F is still degree 2. H is still degree 2. G went from degree 3 to degree 2. We accounted for that there. And H is still degree 2. So let's see. And D is down to degree 1 from degree 2. G is degree 2 from degree 3. Okay. So on that one, we only removed one edge and created a spanning tree. So it was made from a different graph that was previously not a tree. We built it into a tree. I don't think I wrote that up, so let's write that up. If you'll recall from section 13.3, edges, sometimes they're created all the same. So far in this section, we've treated them as such, as if they're all the same. Sometimes they are not necessarily the same. If the edges do have a cost associated with them, we can look for what's called a minimum cost spanning tree. All right, so let's take a look at a complete graph on 4 vertices. So remember, a complete graph just means we have every available edge between any 2 vertices. There are no vertices that are not connected somehow. Here, and now we're attaching costs. So let's see, we'll do AB is 2, AC will make that a 1, AD will make that a 4, CD will make a 3, BD will make another 1, and BC will make a 5. Okay, so there are several spanning trees that exist for this graph. So let's see, we could remove AB. that would still be connected. We would have to remove more. We can remove AB and AC and BC. So here's one possible spanning tree. So cost remaining of 413. Let's see, we could again remove AB, but this time keep BC, and that forms another spanning tree. So cost for that guy, a 4, a 1, and a 5. So I'm going to ask you to pause it and see what else you can create, what other spanning trees you have that are possible based on this one. Okay, welcome back. So let's see what else we've come up with. Again, we'll start with removing AB. And this time we'll keep this guy, and we'll keep this guy. So another example of a spanning tree, and we have, let's see, a 4, a 1, and a 1. And then we can start doing some rotations on those as well. So we can do maybe a mirror image of one of these. So the cost of 4 and 3 and 5. And let's see, let's mirror this guy. A 4 and a 2, and let's see, a 3. And as you might have noticed, there are several. There's many spanning trees. We don't want to necessarily have to use brute force. There are more. So the idea is, instead of finding each one and calculating the value, so just of what we've done so far, let's see, we have a cost of 8, a cost of 10, a cost of 6, a cost of 12, and a cost of 9. So 6 was our lowest spanning tree for that one. But instead of trying to come up with every possible arrangement and testing more, in other words, brute force, we again come up with an algorithm to approximate. So that takes us to our friend Kruskal. So remember, an algorithm, just a set of directions. How do you do this thing? And again, just like most of these algorithms that don't have us going through brute force, it's possible we don't have the best answer. It's just a way to get us to a good answer. So possible we don't have the best solution. That is, I think, the messiest way I've ever written solution. It's possible we don't have the best solution. This is just a way to get a good solution. Maybe it is the best, maybe not. We would have to use brute force to get there. Let's see. On this last one, let's see, we had a total of 1, 2, 3, 5, 6 edges, and we're moving 3 at a time. So 6, choose 3. And we'll take a look at these a little bit later on. There are 20 ways that we could have removed 3 of the 6 edges. Not all of those are necessarily going to be spanning trees, but I definitely didn't want to draw out the 20 different possibilities and then cut the ones that weren't spanning trees. Kruskall's algorithm will get us sort of close enough to a good solution. So the idea here, select the lowest cost edge. Select next lowest cost edge. This time a restriction though, that does not form a circuit. Continue until graph is connected. Then go ahead and calculate the cost. What is the cost? All right, so this one we'll look at 5 vertices. And we're going to go ahead and make it a complete graph on 5 vertices. I'll make my vertices a little bit fatter just so that's clear what's going where and the degrees a little easier to spot. Okay, so let's see. So we'll name this guy RSTUV. And our costs. Let's see. So we'll do 1, a 2, an 8, a 4, a 5, a 3, and this guy will also make a 3. Let's see, this guy will make a 9, and let's see, who doesn't have a cost? RT doesn't have a cost. We'll set him up as a 6, and then let's let's see, so everybody on R has a cost, everybody on S has a cost, everybody on T, not everyone on T, we need VT, and we'll make him, let's see, he'll be a 7. Everybody on U is good, so everyone on V must be good. Okay, so there's our graph that is weighted. We have a weighted graph. Each edge was weighted. So on this one, instead of removing edges, this time we are adding edges. So I like, with Kruskal's algorithm, I like to just kind of start a new one. So here's R, here's S, here's T, here's U, and here is V. So there's our sort of blank. We don't have any edges yet. And we'll listen to Kruskal's algorithm. Our lowest cost here was a 1. So RV is going to be part of our spanning tree with a cost of 1. After that, I have a cost of 2, and it doesn't make a circuit, so I can use it. Then I look for the next lowest cost, and notice there's a couple that have a cost of 3. There's one I will use, one I definitely wouldn't touch. I definitely don't want this 3. The reason being is, if I do choose that one, I've made a circuit. Our direction said, don't make a circuit. Do not form a circuit. So I don't want that 3. I do want this other 3. So RU will be put on there. And that's a 3. Okay, so we use that guy. Cost of 4 looks like U and T. And that's enough for us to be connected. We now have a connected graph. So this one has a cost of 10, whatever we're counting. So whether it be dollars, miles, seconds, whatever it was, this is the lowest cost to connect this graph, at least according to Kruskal's algorithm. It might not be the best, but it will definitely get us close enough without having to, again, go through this idea of, let's see, how many we had to remove, without having to go through all of the iterations of drawing every possible spanning tree and using brute force to find it. This is a way to get us, again, reasonably close. So some homework problems I would recommend. This is section, again, 13.4. I would try out 1 through 6 all, and then I would try 7 to 31 on the odds. If you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.